everybody. Welcome to the first in a series of talks that we're going to have in the next few weeks. Ankit Singla is here visiting us, and his title of his talk is actually very interesting, Jellyfish, Networking Data Centers Randomly. I guess the jellyfish has something to do with its versatility or something, or
it's fluid,
the fluidity or something. Okay, so I'm very excited about that. Let me just tell you, Ankit is a PhD candidate in computer science at University of Illinois Urbana-Champaign. He received his bachelor's in technology, computer science at IIT Bombay, which is a great place. I spent some time there. In 2008, he is a winner of the 2012 Google PhD Fellowship. And we were discussing this actually over dinner last night. He's refining a plan for building a speed of light internet, which he loses no opportunity to talk about, which was true. We had a very good discussion on it yesterday. So please, welcome.
Thank you, Magda. So I see that this is being recorded. Do you need me to wear a microphone or something?
Or I think mic is somewhere.
As long as you talk that loud, you're fine,
Right.
I think.
It's around that area, so
Sounds
yeah.
good? Yeah, I think I'll be loud enough.
Exactly.
All right, so welcome to my talk on wiring data centers randomly. This is joint work with my advisor, Brighton Godfrey, and collaborators, Jiao Hong, Sangeeta Abdujoti, Alexandra Paula, and Lucian Popa. Every large internet service you use today, Google, Facebook, Amazon, everything runs on such infrastructure. Not only do these things support user-facing applications, but these are also platforms for other services. For example, Netflix works on Amazon's web services. So you can use these services, these platforms, to build a supercomputer on the cheap, thousands of dollars per day instead of in expense of millions of dollars, right? Apart from these things, it's being used to run scientific simulations like those for climate change, for the discovery of cures for diseases, for simulating energy efficiency of buildings, even mapping out the course of wildfires, predicting what the next thing will be, and so on, right? All of this is running on data center network infrastructure. So the role of the network in this is to tie together these tens of thousands of servers, to wire them up to solve problems effectively, right? If the network is a bottleneck, compute tasks will be waiting for the network IO to finish before making progress, and that slows down jobs. So the network really is, in that sense, fundamental to this whole cloud computing model that we use. So let's look at what the network is. Essentially, all of these things are built in this fashion. You stack together compute elements or servers in a rack. So this is the granular atom for such infrastructure. On top of such a rack sits a top-of-rack network switch. All of the servers are wired to this switch, right? And then the data center itself has several of these racks, which are connected together in a network. As I said, you'd like this network to provide high throughput because you don't want compute tasks to be bottlenecked on network I/O. So one such case that illustrates the need for this high throughput comes from Facebook. This is a period of time on the x-axis, a little more than a year. On the y-axis is traffic volume. No absolute numbers, of course. Facebook isn't going to tell you that information. The orange line really is the focus here. That's traffic within Facebook data centers. So traffic between servers in the data center. While the other two lines are traffic to and from the internet. So as you can see, the traffic within the data center really dwarfs everything else and is growing at a very rapid clip. So that really indicates that these big data tasks need high throughput, right? You have this ever-growing traffic volume that you want to move between servers. Apart from being an enabler of such big data analytics, the network also provides flexibility in task placement. If you have a high-capacity network, that means you can put tasks anywhere. You can place your virtual machines anywhere in the network should be able to take care of it. You don't have to worry about placing VMs in virtual machines in a certain way so as to adhere to capacity constraints. So this is something people care about. James Hamilton, who's VP of Research at Web Services, Amazon, has said, for example, that I don't want to worry about this problem. Get the network out of my way. Just build it as best as you can. I don't want to deal with the scheduling issue. So in summary, we need big data networks, high throughput networks to support big data analytics and to ease virtual machine placement. Now we want to solve these problems as the network grows over time. These things are not static objects. As your application grows, as your user base grows, for example, if you're Facebook, you might need to add more servers. You might need more network capacity, for example, if the application's bandwidth needs change. So you might need to add racks of servers or just switches, and the network needs to be able to absorb these elements seamlessly. Apart from this, so in Facebook's case, this is very clear. You can see the server footprint, no absolute numbers again, growing over the years. They say they're adding capacity on a daily basis. This is a useful strategy because you don't want to spend all the money anticipating some future need. You want to spend money for what you're using today, and you'd like to augment that as you go over the years. So that's really the goal here with incremental network expansion. Now, as you grow the network over these years, the newer equipment that comes in might be different from what you already have. Switches, for example, might have higher port counts. Every year, switch vendors come up with, now the number is, I think, 128 ports per switch. So the number of connections that a switch supports in a non-blocking fashion increases. Line speeds grow. Now people are looking at 100 gigabits per second. 40 gigabits per second is rolling out into commodity switches. 10 gigabits per second is pretty common already. So all these changes are happening. You'd like this equipment to be seamlessly incorporated into the network. To summarize our goals, design high throughput networks while solving the problems of incremental expansion of the network as well as heterogeneity. Heterogeneity in terms of network equipment that you're wiring in. So how are people building these things today? Right? The traditional design looks something like a multi-rooted tree. So you have at the bottom here servers connected into racks and to their top of rack switches, which are further connected to some switches and so on in a hierarchy. Now, usually these switches at the top of this hierarchy are the biggest ones. They either support the highest line speeds or they have the largest number of ports or such. And the switches at the bottom are the smallest switches. So this is fairly typical. One example of such an organization is a fat tree. And this is one of the designs. Many other possibilities exist, of course, the torus network, the hypercube, all of these designs. One thing that is common to all of them is their neat symmetrical structure, right? Now, structure is nice because it gives us some intuition for design, but it also has drawbacks. For one, all of these things can only be built at very coarse design points. A hypercube you can only build at power of 2 sizes. Other networks have similar design constraints. Also, it's not clear how you'd expand such structure topologies. If you think about a hypercube, for example, you have this neat symmetrical object, and now you have to add more nodes, more servers, more switches. How do you do that? It's not clear how you maintain structure while doing incremental expansion. Other problems that structure causes include the use of identical switches. All of these topologies depend on using identical equipment. All switches look the same. So what do you do with heterogeneity? In the hypercube example again, each node here has 6 connections. 6 is the degree of this network. What happens as you get something larger? How do you incorporate these things? So our solution to these problems is to forget about structure entirely. If structure is hard to maintain in the face of incremental expansion and heterogeneity, throw away structure. Let's have no structure at all, and we'll maintain the lack of structure as we grow. So that's the rough idea. And because structure intuitively makes certain things easier, for example, routing or cabling become easier with structured topologies, I'll describe our solution in 3 pieces. One is the network's topology, what switches are connected to what other switches, and then we'll move on to routing. How do you do routing over these unstructured random graph-based topologies, and how do you do physical wiring for these objects? So let's look at the network topology first. The topology is fairly traditional in its organization into racks. The difference is the switch network is itself a random graph network. So these connections are picked uniformly at random in a particular model. So random regular graphs is what this graph object is. The topology is a random regular graph at the switch layer. What does this look like? This is one example, a little more than a 400 servers Jellyfish network. We are calling it Jellyfish because it makes capacity, instead of a structured solid, more fluid and flexible. Now, these red elements in the center are the switches, and the gray things at the corners are the servers. So this is one example topology. Conveniently, it also looks a little bit like a jellyfish. So how do you build and expand such networks? The strategy is very simple. Let's say you have a jellyfish network to begin with. you see some new nodes coming in. You pick an edge uniformly at random. You'll break it. Now you have free points to connect the new element to. That's what you do. And you can repeat this process ad nauseum as required. You can wire up any type of equipment. The same procedure works for both initial construction as well as expansion of the network. And obviously it's flexible. This thing can have any number of ports. You can add any number of elements. Yes?
Sorry, I thought it was a random regular graph, but that, oh, yeah, one of those I just has 3 and
Yes.
some have 4.
Yes. So this is the model we started with. So I'll describe 2 different things here. One is the homogeneous case where we are working with expansion, but everything looks the same still. I didn't worry about drawing the edges the right way here. But then we'll also address the problem of heterogeneity later. So there it'll no longer be a random regular graph. So it'll make adjustments.
So you have no
Yes.
constraint to the number of, sorry, you have no constraint to the number of ports, right, on the switch or?
So whatever equipment you have, you remain with that equipment. So the number of connections here does not change, right? It had 3 ports to begin with. It's just using those 3 ports differently now. Yes. Okay.
What the node corresponds to essentially a switch. In this
Yes,
case.
yes. In this case, it's just a network switch. It's not, you don't have expansion stuff available on it, that kind of thing. Yes.
Probably you might explain a bit, why do you do random?
Right, right. I'll come to that. So a big reason, the way we started thinking along these lines was because structure constrains these problems of expansion and heterogeneity. It's not clear how you add those elements in. With randomness, it's just a different random network as you're drawing. Yes.
I suspect that some of the results from the P2P world, which
Absolutely.
deals with uniformly random connectivities and ability to deal with dynamicity in
Right,
those situations.
right, right.
carries
So
over.
random networks are very resilient, and for that reason, people have proposed their use in peer-to-peer network design. One thing that people there try to do is accommodate distance constraints. So you don't want random edges from here to Australia, for example. So that is something that we don't have here. We can work with a uniform random model because these are all sitting on a data center floor. They're not very far from each other. So the setting is a little bit different. The model of randomness really makes a difference. We have results comparing various different models. I won't be talking about them here. Small world networks, for example, don't do as well as uniform random networks and so on. So that's something that matters. So anyway, with this simple idea, we can have 60% cheaper incremental expansion than comparable techniques for traditional designs. So people have tried solving this problem on tree-like topologies. Our solution is 60% cheaper. I won't delve into the details for this. The result I'll focus on more is about throughput. So apart from being easier to expand, somewhat counterintuitively, such networks built randomly achieve higher throughput, higher capacity than structured designs, 25% higher than state-of-the-art fat trees, for example. Now this I'll delve into a little bit more, but first I have to describe how we measure throughput. What is this metric? What do we achieve 25% more of, right? So let's look at how we are measuring throughput. You can think of the network in the abstract as a graph here, and you're given certain pairs of nodes that communicate with each other. These green nodes, for example, might have flows or traffic running between them. And you have several such pairs of nodes that communicate, right? Now, the throughput metric we define is a maximization of the minimum flow in this network. Why the minimum? Because you want some notion of fairness. You don't want some flows to leave all the throughput. For example, you could think about measuring the aggregate flow in the network. But then you might have certain flows that achieve very high throughput while others languish, right? So you don't want that kind of discrepancy, and that's why we maximize the minimum flow. It's a fairness constraint, very tight fairness constraint actually. The particular sets of nodes that communicate, that defines the workload. And yes.
So I totally agree that fairness is important, but
Right.
you wouldn't want to give up too much of the global flow in order to...
Right. So that's a perfectly reasonable point and something we think is an important direction for future work. For example, I would like very much to say something like maximize the 95th percentile flow, right? That would be a little more middle ground in terms of you don't want poor flow fairness, but you also don't want to constrain yourself for one bad flow in the network, right?
Sure.
Unfortunately, that does not fit into the linear program model that we use to
Okay.
model these things. So we make some relaxations there.
Sure.
But that sort of thing does factor in well into the actual packet simulations that we do. So we'll look at that metric as well, and it'll accommodate the kind of thing that you're suggesting. Right. So the particular sets of nodes that communicate here will be our workload, right? What is the workload that we are measuring this flow over? That's the same as what past work has used, either all-to-all traffic, so every node communicates, every server communicates with every other server, or random permutation. So pairs of servers communicate with each other, the pairings are picked as a random matching. So these are the same traffic matrices that past work has used. Factories, for example, use random permutations. Microsoft's work has used all-to-all traffic. The reason people use these traffic matrices is because there's no notion of a typical traffic matrix for a data center. Even if you knew things, for example, like 20% of the nodes or servers produce 80% of the traffic, it's not clear that that helps you very much. As long as you're unable to say which 20% nodes will produce that traffic, you have to design for uniformly high throughput. And that's why these metrics make sense. In our work, we extend this to also talk about throughput under nearly worst case traffic matrices. So finding the absolute worst case traffic matrix, the matrix that minimizes throughput for topology, is an NP-hard problem. But we can have heuristics, which we build in this work, that get pretty close to that worst case. Again, I'll not talk about these results, but the bottom line is the random topology beats factories and everything else on this set of traffic matrices as well. I'll only be showing comparisons here against a couple of topologies, but in this work there are comparisons with 10 other topologies, and everything else is inferior to the random graph-based network designs. Yes?
Are you making assumptions about the link bandwidth?
Yes. So far, the setting I'm describing, everything is uniform in the sense that all links are uniform line speed, 1 gigabits per second, let's say, for example, that kind of thing. The flow demands are all uniform. Everything is uniform in that sense, yes. So in some of our work, we have addressed that question of line speeds, but I'm not able to accommodate that in the talk. Sorry. Yes.
So maybe I'm not getting the intuition correctly yet. If I have a structured network,
Yes.
which I do know about,
Yes.
I can do placement of my
Right.
processes and my
Sure.
workload to maximize the benefit of a structured network. If
Sure.
you replace it with a random network,
Right.
I don't know what to do at this stage.
This is a perfectly
So-
reasonable point, yes.
So the question is, when you compare
Right,
the throughputs,
right.
you need to compare basically the
Placement.
best that I could get out of
Sure,
a given
sure.
structured network, right?
So for any way of placing these random permutations or anything that you have here that we are comparing, you won't get any difference. For the random graph, for example, any random permutation achieves the same result. The variance is very small there.
Right.
The factory-like topologies are built in such a way that the distance between any pair of communicating things is the same. So in that sense, it doesn't matter that much. Although, if you knew what your application's traffic matrix is going to be, you can do much better than either the generalized factory or that kind of topology or the random graph. So if you had that knowledge, you could do much better.
Yeah, but if I go back to the thing that you were saying, that you
Right.
want the CEO of Amazon to not worry about basically the
Right,
network
right,
at all,
right. Yes.
then you're not taking that away. Being worried about the network topology actually does help, and that's not the problem that's being disappeared, right?
So you worry about the network topology in the sense that you want it to be as generic in supporting anything you throw at it. That's all we want to concern ourselves with. We don't want ourselves to worry about, if I throw in this application, will it work well? You want to you have to over provision it a little bit to make sure everything fits. So you're sort of doing a worst case like design.
So you're doing it for more generic workloads.
Yes. And also, think about it in this way. Let's say you have a structured topology. You're running a cloud network. You have lots of tenants. Now, all of them have used certain capacities at compute capacities at nodes, and network traffic is using capacities at edges. Now, if you think of the abstract view in this scenario, it doesn't look that uniform. You have to solve the same problems again in an automated way. So you don't have that structure preserved as people use some of that capacity. So it's really not that different in terms of setting. Yes?
One more question, excuse me. Do you worry about latencies at all?
Mm-hmm. So latency is roughly separable into two parts in this setting. One is that caused by path lengths, the propagation delay, so to say. Path lengths we show here are actually smaller than the factory. And that's something that I'll discuss in more detail pretty much immediately after. The other aspect is queues at routers, queuing delays, right? So that's somewhat separable because people have solved that problem in the transport layer. So people have various schemes that are topology agnostic that keep your buffers small. So it's separable into those two pieces. The latter piece is handled at the transport layer. The former piece I'll talk about in more detail in just a moment. Yes?
How you handle like not leaving the network?
Sorry, I
How
didn't
do
get
you
that.
handle not leaving the network due to
Node leaving the network.
yeah
So
Failure.
the failure or intentionally like
right.
taken down?
intuitively, the node leaving the network does not make much of a difference. It's just a smaller random graph as one less node. We also do experiments to check this out. It turns out the fat tree is less resilient than our topology. The rough intuition is that in those topologies, some nodes tend to be more important. For example, the root switches, if one of those things fails, you lose much more than you lose if something at the bottom fails. So failures are not all the same there. Here, failures are all the same. You don't lose as much if anything fails.
I think
I
we
should
should
really,
go on,
yes. Sounds good. But yeah, I have a reasonable amount of time for questions. Feel free to shoot throughout the talk. I might defer longer discussions to later, but we'll finish in the hour. Don't worry about lunch. It'll be fine. So on the x-axis here is, so I sort of jumped the shark here. So now with this metric settled, let's look back at the result in a little bit more detail, that 25% number, right? On the x-axis here is the network's cost. This is being measured as the number of ports that you're investing in. So if you buy 50 switches, each of them has 10 ports, the network's cost is 50 times 10, 10, 500, right? So that's the metric on the x-axis. How many ports are you buying for the network? On the y-axis is the number of servers that you can connect to this network while ensuring that every pair of switches, every pair of servers can talk at full line rate. So there are no bottlenecks. And this is with regards to those traffic patterns that we talked about, all-to-all traffic or random permutations. So when we do these comparisons, we find that the Jellyfish random graph topology beats the fat tree by 25% at a fairly small scale, 3,000 or so servers. And this gap is actually increasing with scale. We're limited in what we can simulate by computational constraints. So the gap increases with scale, and at a fairly small scale, you get a 25% gap. I'll stress that the equipment being used here is identical. Both networks are being built with the same switches and servers, same number of cables. They're just wired differently. One is wired into a factory-like topology, one is wired into a random graph. So that's the key thing here. The networks are being compared apples to apples, and you get this 25% throughput. So we can beat structured designs, which were carefully engineered over the years with this random graph topology. Why does that happen, right? So we'll spend some time looking at the intuition for this. Was there a question there? Yes?
Yeah, this was number of ports. How many switches are we talking about?
So in this setting, we are using the same thing. So the factory topology is defined completely by one parameter, which is the number of ports on each device. So the number of ports are increasing on that graph on the y-axis. Here we have something like 6 ports per device. At this end, we have 18 ports per device. So it's all even numbers in between. Right? Okay, so where does this gain come from? I'd like to give you some intuition. Yes?
I find it really hard to believe that the hierarchy does not scale better than the random graph. So one key thing is that all your switches in the hierarchy are similar to the other ones. So in reality, in actual networks that do the hierarchy,
Right.
you know, as you go up in hierarchy, you should have more fun.
Higher, bigger switches,
And
right?
second,
Yes.
how about the link bandwidth?
Yes. So we'll address both these points when we talk about heterogeneous networks. So I'm addressing the simpler homogeneous case right now, and I'll come to how we deal with heterogeneity. You'll find that the result is actually counterintuitive. These networks, the gap actually increases when you use heterogeneous equipment, but I'll come to that in more detail. All right, let's look at intuition for why we do so much better. So think of the network again as this abstract blob, and let's say this is the shortest path between these two blue nodes, right? If you want to send traffic between these two nodes, you have to occupy capacity on at least this many edges. That's the shortest path. Now, if your network provides a shorter path between those two, if it did, you could use that path and leave those edges spare for other flows. In summary, shorter paths in your topology translate to higher capacity. So this is with the proviso that your topology doesn't have small cuts. and we'll account for that at some later point. But this is the rough intuition. For networks that are smooth or uniform in some way, shorter paths lead to higher capacity. So here's an example that shows clearly our topology has short paths. No, it doesn't show that clearly, but we look at a somewhat more easy to understand example, and I'll follow along step by step. Here we have two topologies, battery, jellyfish, random graph, both built with the same exact equipment. We'll pick a random origin server, an arbitrary origin server, and we'll look at the distances to other elements from that server. So again, the red things are the switches, the gray things are the servers. So in one hop, you can reach no new servers. You are only able to reach one switch in both topologies. 2 hops, 3 hops, 4 hops, 5 hops. In 5 hops, in the factory topology, you only reach 4 of the 16 servers, while in the random graph, you reach 12 of 16 nodes. Now, for anyone who's familiar with expander graph theory, this is not a surprising fact. Random graphs are known to be good expanders, and this is what gives them their path length characteristics. What is happening inside the factory is very interesting though. All of these edges, the ones that I've colored red, they're being wired in a way to add redundant capacity, but they're not doing anything at all to shorten path lengths. In fact, if I throw away all of these edges, I've thrown away most of the network at this point. Something like 3/4 of the edges are gone. The path length characteristics between any pair of servers do not change at all. The path length distribution for this graph is the same as what we had with roughly 3 times more edges. So these edges are just not wired in the best way possible in terms of reducing path lengths, and that's where the game comes from. You can look at this in a larger example as well. Here we have something like 700 servers, a factory. This is the path length distribution. Most pairs of nodes are at distance 6 from each other. While in the comparable random graph topology, most nodes are at shorter distances, 4 or 5. We also find that the diameter of these networks is actually either the same or smaller than factories. So that addresses the latency question with regards to path length, at least. So that's where this game comes from. Now, this, again, we've beaten a carefully structured engineer design with a random topology. What does this mean? Can we go much further? How much room is there for improvement? If we have improved by 25% on this carefully engineered design, how much room is there? How far are we from optimal network capacity? Right? This is the question that we want to address. While it's NP hard to build the optimal topology, otherwise we would be doing that, we can build an upper bound, right? And the intuition for that upper bound is the same intuition that we described for what gives topologies higher throughput, right? Shorter paths lead to higher capacity. We can formalize this intuition and find that throughput is inversely related to mean path length. Now keep in mind that this is an upper bound. Cuts will give you another upper bound, and that might be tighter. We'll think about that later. But this is one upper bound. Throughput is bounded by mean path length. If you lower bound mean path length, you can upper bound throughput. Quite conveniently, Windsurf, funny t-shirt model guy, Windsurf, that name should ring a bell. So Magda will love this.
Yeah. Thank you.
Now, yesterday we were having this discussion about people not appreciating work that was done in the 60s and 70s. This bound is actually from 1974. So we did do our due diligence there at least. So we translate that bound. Surf gave a bound on mean path length, lower bound on mean path length. We translate that into throughput and compare it against the random graph. On the x-axis here is the network size. On the y-axis is throughput as a ratio to the upper bound. So we are measuring how well we are doing in comparison to the upper bound. We find that across these traffic matrices, all-to-all or random permutations, the random graph achieves throughput very close to the bound, within a few percent of optimal. So putting this result in context, what does this mean? We've had a series of topologies proposed over the years for these networks. And I've excluded here work from the 80s. I apologize.
I'm just kidding.
I'm picking on you for last night's hammering.
Okay.
So yeah, she really gave me a hard time about, people ignore all this stuff. So no, we don't ignore all this stuff here at least. So topologies like hypercubes, for example, people had been building them as far back as the 80s. On-chip networks, people had lots of designs. We compared with a bunch of stuff. we find that not only does our topology proposal beat all these things in throughput, what we're saying here is something stronger. What we're saying is you can't go much farther. You can't improve upon these topologies, at least in this one dimension, much further than this. So that's the result. So the lesson is focus on other things, please. One dimension that we focused on is heterogeneity. How do you address heterogeneous network design? Now that you've tackled this problem of homogeneous network design, what do you do here? So far we've looked at settings where everything looks the same. The switches in the center are all the same. The servers on the edges are all the same. What if you have, let's say, instead of these 2 types of components, 3 types of things? Servers, switches, and some switches with larger port counts, right? Our general strategy for talking about this kind of setting will be to sort of logically cluster these things into homogeneous clusters, which we'll talk about the connectivity between these clusters. And then we'll fill in the gaps, fill in the blanks using randomness. So that's our overall strategy. Now the setting we'll work with is some low degree switches, so these have fewer ports, some high degree switches, and some servers. One question that we want to address is how should we distribute these servers across these switches? Should we connect more servers here on the smaller switches or more servers here on the larger switches? The second question we want to address is how should we interconnect the switches? Should there be a large number of connections across the 2 types of switches, or should there be richer connectivity within these clusters? So these are the things that we want to talk about. Let's look at the first one. As I said, there are several options here. You could connect all the servers on one extreme to the small switches. At the other extreme, you could connect all of them to the larger switches. And in the middle, there is the spectrum of options, right? On the x-axis is exactly this spectrum. Don't worry about the label. And on the y-axis is throughput. Throughput, we find, is maximized when you distribute servers in proportion to switch port counts. For example, if you had 2 types of switches in your network, 100 ports and 50 ports, add twice as many servers to the 100 ports ones as you add to the 50 port ones. Now this is very simple, and we verified this across a wide variety of parameter settings, tens of them, different network port counts, absolute ratios, all kinds of things. And it's also an intuitive result. The kicker is that networks aren't built like this today. If you refer back to our canonical topology, these are the smallest switches that have all of the endpoints connected to them. The larger switches sit at the farthest possible distance from the traffic generating elements. So it's completely upside down in that sense. So we need to fix this. This is one of the lessons we'll apply when we think about redesigning such topology. So we'll come to that. But first, let's talk about how we interconnect the switches as well. So again, here there are several options. One is to not have any connections go across these 2 types of switches. This is obviously a stupid idea. Your network is disconnected. But I have stupid ideas too. It's fine. So your network is disconnected, throughput is 0. You're doing nothing smart here. On the other extreme, you can build all possible connections across these 2 types of switches, like a bipartite graph. And in the middle, of course, sits this spectrum of choices. On the x-axis is exactly the spectrum. On the y-axis is throughput again. What does this look like? Should this look like our distribution of servers, or perhaps this or this? The answer is much more nuanced and interesting. We have this sort of linear increase period and a plateau. And we verified that this checks out across, again, lots of parameter settings. One of the optimal choices, or throughput maximizing choices, is the vanilla random interconnect, where you just look at ports as ports. You don't think about, oh, this is a port on a big switch or a small switch. You just wire up ports randomly. So that is one of the throughput maximizing choices. We understand this result much better than we understand the other result. The other result is intuitive. The result on distribution of servers, we don't have a theoretical proof for that. It's simple to state, it's intuitive, but the proof of that has escaped me so far. I'm interested in coming up with it in the future. Yes?
So just to sort of recap, am I
Yes.
understanding it correctly that if I distribute servers in proportion to the number of ports on the switches, I do get the same overall result as if I did a random interconnect between the ports, not counting the switches?
So there are 2 separate problems, right? One is the distribution of servers to switches, so those connections, and then the network connections.
Between
Between the switches. So you have to address both things separately. Yes?
So it's very different to say that you're going to distribute connections randomly versus distributing them not quite arbitrarily, but I mean in the
Right.
in the real world, I will respectfully disagree with Sharad and say, when it comes to sysadmins, it would be nice if we could let them be lazy. Like, here's a new node. Oh, look, there's a port right here. What have happened? I mean, that's not random. It's not quite random
No,
to say, I'm just going to use the shortest wire I can, connect to the nearest
That
guy.
won't work very well. That is not a recommended setting. So humans are atrociously poor at randomness, and we can talk about this in a bit more detail. Like, there are tons of anecdotes I can tell you that, of course, I didn't come up with. My experience
Right,
on
so
this planet
it
is
does have to
limited.
be more formally random then.
Yes, it has to
Okay.
be more formally random.
Okay.
You'll generate a blueprint and tell people, here, wire this port to this port. Don't do anything else. Don't try to be sneaky with me.
So I
Yes.
understand your result correctly. So this is under the assumption that the servers have been placed in proportion to the
Yes.
Oh, I
output.
see,
Yes.
I see.
It's a
Okay.
result
So,
of that, right?
yeah, I separated out these two results,
Yeah, but
while
this is the-
actually
yeah.
it is a joint optimization problem.
Right.
We do simulate, so for that setting, we don't have crisp answers, as in distribute servers proportionally and do this. But that turns out to be one of the optimal choices. If you do both of these things that we've talked about separately, distribute servers in proportion and wire the ports up randomly, that turns out to be one of the throughput maximizing choices. But there are some more choices, some different combinations of these things that also work. So I've sort of cheated a little bit by separating these out, but it keeps the discussion simpler. Yes. All right, so this result we understand much better. We have good bounds on this. We have an upper bound which is very close to the empirically measured value. In a special case, we can actually also prove a constant factor matching lower bound. So we really have quite a good handle on this. What's happening here? Let me give you some intuition for that, right? We have a period of linear increase here where the throughput is determined by the sparsest cut in the network. So the smallest cut determines the throughput, and the smallest cut is the one across these clusters. So if you had 0 edges, throughput would be 0. And as you increase the number of edges across these two types of switches, the throughput increases linearly. While once you hit a certain point, the average path length becomes the constraint. Like we discussed, networks with smaller average path length have higher throughput. And as you increase the number of connections across these two clusters, while decreasing the connections within, the average path length doesn't change very much. So that's why throughput flattens out. So this is the rough intuition for what's happening here. Now this has some interesting implications. It provides you with a wide range of connectivity options. For example, you could have a large cross-section across these two types of switches and very sparse connectivity within. Or you could have a large amount of connectivity inside at the expense of a much smaller cross-section. Yes?
So you say by random, like they're gonna like utilize all the resources that the data center, like I see in the picture, like some server left out without connect to other node.
Right, this is just me being lazy in terms of not having drawn all the edges. It's boring.
No, I mean like,
But you will use all ports available. You won't do this.
okay. So,
I will hope that you pay your sysadmins enough to not be lazy.
Facebook does.
Yes. So yeah, forgive my lack of concern here. So these two settings, one with a sparser cut here and the other one with a richer set of connections here, give you the same throughput. What this means is, for one, bisection bandwidth, which people often use as a metric, is not the same as throughput. We can show networks where one has higher bisection bandwidth and the other has higher throughput. So we have theoretical constructs that do this. Now that said, lest you think all of this is an accounting trick, I want to mention that our networks beat factories on bisection bandwidth as well. So that's not what's happening here. Every time someone defines a new metric or says they're using a metric, you should be suspicious. What about the other thing, right? So we do beat them with similar margins on bisection bandwidth as well, but really our recommendation to network designers is stop using this metric. Bisection bandwidth is a cut-based metric. People's intuition for using those as proxies for throughput comes from the idea that cuts and flows are the same. That is true only for one, or people have actually extended that result to 2 source-destination pairs. But as soon as you're talking about large numbers of sources and destinations, the max flow min-cut theorem does not work. That is not something that applies to that setting. There can be an order log n gap, where n is the number of sources destinations you have. So need to be careful with using this as a proxy for throughput. The second interesting thing is this allows us much greater freedom in cabling. You can, as I said, you have different cabling arrangements. You can have a larger number of connections in one cluster versus going outside. So you can trade that off with losing very little throughput, and you'll do much better on cabling. So you'll use this insight later, the freedom in cabling, to build practical cabling schemes for these networks. All right, so keep this in mind. And now we'll apply these lessons to improving a real heterogeneous topology design. So this is the VL2 topology. This is deployed in some of Microsoft's data centers. As Athena pointed out, this is typical in that you have some higher degree switches here. You have some smaller switches closer to the bottom. And then you have top of rack switches, which we will treat as servers in our discussion, because people think of these as sort of atomic units. You don't want to throw around servers. You don't want to distribute servers across your data center. We'll talk about distributing top of rack switches for two reasons. One, these are the only elements, these two elements are the only things that have 1 gigabit per second connectivity, or the smaller line speed. And then everything else up here has higher line speeds. So it really doesn't make sense to connect something that has smaller line speed on these ports. So for these reasons, we'll think of these as atomic units, and we'll distribute top of rack switches in proportion to the degree of these two types of switches. And then we'll build a uniform random interconnect between these two switches, these two types of switches. Doing this simple thing gives you 40% better throughput than the VL2 topology. Yes?
So in that previous configuration, is
Yes.
the assumption that every one of those atomic units is homogeneous?
Yes. Yes. Yeah, we've cut some corners on how heterogeneous we can deal with. It would be nice to extend our results to multiple types of heterogeneous. We haven't gotten there yet. So this simple application of the lessons that we learned gives us 40% improvement. So that wraps up the topology design segment of my talk. Now, I want to address this question of routing, right? Intuitively, if you looked at this structured topologies, it's very easy to do routing. For example, between these two servers, you have a set of paths that you can intuitively point to and say they are similar in some sense. They have the same path lengths, their neat structure. The topology structure allows you to pick these paths out very easily. You can install these using commodity protocols like equal cost multiple path, and it gives you nice throughput. The question arises, how do we efficiently use the capacity that we said the graph, the topology has with realistic routing? In theory, this is very easy. This is just a multi-commodity flow problem. But in practice, this has several challenges. One is, how do you solve this linear program for the flow problem using a distributed protocol? And two, the optimal solution can have lots of flows. This is the splittable flow model we are working with. You can have 1,000 little flows running through your network. Good luck with installing all the routing table rules for that. So this is not really something feasible. Our solution, though, is, the solution is very simple. Just pick for every pair of source destination switches a set of shortest or near shortest paths. So pick either shortest paths, or if you have too few of them, you can pick some paths that are longer by 1 hop or so. Install these using whatever means, OpenFlow, MPLS, virtual LANs, lots of different options will let you do this. Switches today have enough routing table entries, 128,000, 256,000 is not that uncommon. You can do this. And then let multipath TCP do the rest. So this is a protocol at the transport layer which spreads load across the set of paths that you've chosen. So if your flows are competing on some edges, it will move the traffic to the other paths in your list of choices. So we're happy to stand on the shoulders of giants, and if you've met this guy, and he's very tall, Mark Andrew, tall guy. So doing this simple sort of idea gives us very high throughput. Routing is very efficient. The flows model is the linear program solution, so that's with optimal routing. And the packets is packet level simulations with this simple strategy. So we get just within a few percent of optimal routing. Very simple solution. So we can do efficient routing. In fact, the result I showed you with 25% gap, that actually is the result of packet simulations using this strategy. So the minor inefficiency is already accounted for in there. Okay, so we can do efficient routing. Now let's talk about cabling. To begin with, this does not look promising. Let me just sigh here and say this does not look promising. It bears more than a passing resemblance to a bowl of spaghetti with some meatballs thrown in for good measure. Appetizing, but not something you want in your data center. Again, we will have lunch in time, I think. So this is not something that is what you want to build. You do not want to deal with this mess. So what do? For one, we can point out that you can interpret our results as you can get more servers in at full line rate for the same switching equipment, or in another sense, you can get the same number of servers with fewer switches and less network cables. You can have fewer cables for the same number as the factory, but this is not enough. You might have fewer cables, but it's still a mess. So we want to go further, right? We want to talk about physical organization. What you can do is use a similar sort of strategy as people do for building structure designs. You partition your network into clusters. So these are multiple racks that are sitting together, 5 per cluster here in this example. And then you run aggregate bundles between these clusters. So you don't have individual cables running amok across your data center floor. You consolidate cables that run between clusters, and you can have neat cable organizations. So that's fine and good. But you still have this concern that you might have a large number of these long cables. Long cables are expensive for this reason. As soon as you step across this bound of roughly 10 meters or so in length, Ethernet over copper cables turns out to be woefully power inefficient. It dissipates too much power, copper dissipates too much power, and you can't use it. So you have to switch to optical transceivers, optical fiber, and that costs $200 more than the comparable copper cable. Immediately, the cost of those transceivers at the end adds this amount of money. And as you can imagine, with such a large number of cables, this can be a significant expense. So you don't want to do this. So what you've decided with the physical organization is you have these cable aggregates. Now you want those cable aggregates to have smaller numbers of connections as well. Just the physical connections, just the consolidation is not enough. You want fewer numbers of connections. So here is where our insight on cabling comes back in. So you can have these clusters, and you can run a smaller number of connections between clusters while having richer connectivity inside, while not losing much throughput. So that's the insight we had looked at, and that's what helps us here in this practical cabling scheme. We do exactly this, run fewer cables across clusters, more cables within clusters. And we find that throughput drops very little as you localize the cables. On the x-axis, let's not worry about details, we have to hurry a little bit here. Then you localize 60% of the cables. So 60% of all cables are within individual clusters. You get 6% less throughput than the optimal vanilla random throughput. Now this is better localization than the factory. In the factory, you have to have 50% cables go outside the pod or the cluster in their case. So what we have here is a random graph-based topology that achieves higher throughput than the factory and is actually, surprisingly, cheaper in terms of cabling. So you can do both. We have put all of this together in our lab at a very small scale. Done by professionals, but please do try this in your lab. The point of this test bed, it's very small. We still get 3 to 5% better throughput than the factory. The point is not that 3 to 5% gap. That's basically like experimental error. The point is we have commodity routing protocols. We did not modify firmware. We used MPTCP out of the box. Those folks have an implementation kernel level. We use that stuff. We install routes using OpenFlow. Everything works. So this is all stuff you can do today. So that's the demonstration part of it. The 3 to 5% throughput, yeah, it's fine. So, but as I showed earlier, with scale that gap increases. So you will expect to see those benefits. For more details, I'll refer you to our papers on the subject. This is the original Jellyfish paper, which showed an improvement over factories. Here we showed that you can't do much better and handle the heterogeneous network setting. And this is the work on measuring a large number of topologies across a wider spectrum of traffic matrices. But let me quickly summarize our results. For one, we showed that you can beat structured topologies with this random graph-based design. I only described comparisons against factories, but 10 other topologies in the space, everything is beaten by these topologies. You can't do much better than this. So that's also key. In addition, we are able to solve these practical problems, which is cheaper expansion by 60%, 40% advantage over heterogeneous design. Also, we can do efficient routing and cabling of these topologies, cheaper cabling than a structured topology, which is quite counterintuitive, I think. So that wraps up the Jellyfish segment of the talk. I'll take the remaining 5 odd minutes to talk about putting this work in broader context. So I started with this image of Google's Iowa data center. This is only one piece of what makes things work today, right? How a lot of things work is at one end sits the data center, at the other end sits a user like you or me who's making, let's say, a search query, and you have the internet sit in between these two ends. So now I want to, having looked at this piece, I want to focus my attention on this piece, on internet. So what we're working with here is looking to provide low latencies, because the cloud model really is about consolidating all these resources in one place. You have massive compute and storage tied into these giant facilities, but also you want to provide low latency over the internet to these facilities so that those resources seem like they're local to you. So that's why we're working on an internet at the speed of light project. This is joint work with my advisor Brighton Godfrey and Paul Chandrasekharan and Bruce Maggs at Duke University. So today, you can fetch content from across the world in a matter of a second. This image sitting on, well, this was done from Champaign, so your mileage may vary. But from Champaign, getting this image on Wikipedia servers in San Francisco takes me about a second. This is just a small amount of data, tens of kilobytes. We're not talking about bandwidth limited things here. On the other hand, if you were to look at the speed of light latency between Champaign and San Francisco, that's less than 25 milliseconds round trip. So the internet's really quite slow. One second of fetch time seems impressive in the light of what we had. Let me say, 70 years back, in World War II, you were using pigeons. So 1 second for getting data is impressive, but now we care about milliseconds, right? We care about milliseconds now. Amazon has noted that 100 milliseconds of slowdown on their website lose them 1% of revenue. So we care about milliseconds now. 1 second is no longer enough. That's not the benchmark. And there's plenty of room, as I said, for speeding up the internet. This is really the fundamental limit. So the internet takes a second, while the speed of light latency is 30 milliseconds in that example. We found over large-scale measurements that that's pretty typical. The internet is, in the median, 34 times slower. For these small object fetches, we are not talking megabytes of data which would be limited by the bandwidth, right? So this is all about how quickly you can move a few bits or bytes across. So really, this large gap should be an embarrassment for network engineers. We have to move to a speed of light internet. There's no other way. There's a sense of urgency that we need to show as a community. This should be embarrassing for us. 34 times slower, what are you doing? So I want to pitch a speed of light internet as this grand challenge for networking. Not only for this intellectual quest of, oh, this is embarrassing, we need to fix this, but also because it will enable good new applications. For one, it opens up the possibility of instant response time. What I mean here is this. Human visual perception is very limited in the sense that if we see two visual events that are separated by less than 30 milliseconds or so, we can't tell which happened first. So imagine clicking a link on your web browser, seeing the result within 30 milliseconds. It'll seem like magic. You don't have to wait. It's just there. So this is a threshold in user interface experience that we don't have today. Amazon says 100 milliseconds matter. This surely matters. The 100 milliseconds translating to 1% of revenue is an indicator of how much it impacts user experience. So you're not talking about a 100% reduction, 100 millisecond reduction here. We are talking about a 34 times reduction here. So big sort of change. And 30 milliseconds at the speed of light will get you pretty far. So round trip from the center of the United States, you can get to pretty much the entire continent. Round trip in 30 milliseconds. So it's really speed of light is fast, basically, is all that this is. Looks pretty cool. So what does this mean for the cloud model, right? Today, content distribution networks build hundreds of sites across the globe trying to cut latency. Now, if you had just 7 data centers and a ubiquitous speed of light internet, you can reach everyone within this 30 millisecond latency bound. So it really furthers that model along. Also, it opens up possibilities for new applications. For one, music collaboration, for example. This really requires some 30 odd milliseconds or less of latency between the musicians you're playing. In lab settings, people can do this today for short distances, but not something you would try over the internet. I have tried and failed miserably. It does not work. Also, people have been talking about virtual reality. What about teleimmersion? In virtual reality, you're trying to embed yourself in a virtual world with a server potentially that's generating that virtual world sitting right next to you. Now, imagine, you guys are already close to the beach, but imagine from my perspective in Illinois, I could be at San Francisco Beach. It would still be cold because realistically I'm in that room. So tele-immersion really is the illusion of immersing yourself in a remote location. This is one of computing's long-standing dreams. The bottleneck is latency. You really need some 20 odd milliseconds of latency at most to give this illusion. And yes, motion sickness is a problem. People are working on it. We'll see what happens.
I was very sick yesterday when I tried our glasses.
Oh, really?
We have a barrier.
We use immersive display.
So other things, of course, Internet of Things, big thing people have been talking about. If you have these smart objects that you're able to communicate with in some interesting way, for example, you read a tag and it shows you some information. If you want this interaction to be seamless, you really want tens of milliseconds of latency. Beyond that, the interaction will be broken in some way. You'll be waiting on responses or such. What else, I don't really know. The internet itself was not meant to be everything that we use it for today. Clearly, once this is on the way, people will build interesting things on top. For more, I'll refer you to our position paper. Now, at this point, you might put on your skeptic's hat and say, hey, it's easy to write position papers. You sit at your desk and you churn them out, right? And that's pretty much true. Do some calculations and that's what you get. What I'm going to tell you today is that this is not impossible. In fact, we can build this. We have a blueprint, which me and my collaborators have designed for the contiguous United States to build a nearly speed of light network, 10% slower, I admit. That's not much, 1.1x versus 34x. So we have this plan. It's based on using microwave towers. These red dots are actually microwave towers. It will be built at a fraction of the internet backbone capacity, but we can still do interesting things with it. And all this would cost a mere $250 million. This is peanuts when you consider internet infrastructure money. For example, if you think about the internet submarine cable map or a part of it, each of these cables, transatlantic, they cost similar amounts of money, $200, $300, $400 million. One cable is being laid across the Arctic Pole right now at a cost of $850 million. So really, $250 million to cover the entire country, or apologies to Montana and Alaska, is really quite cheap. So our goal should be to make this happen, a speed of light internet, not eventually, but within the decade. So to summarize, my work is about pushing networking to its limits, building nearly optimal data center networks, and a speed of light internet within the decade. Be happy to take any questions. Thank you.
What's the throughput of your microwave?
So it's
network
going to be, the 250 million number is for a design that's 1/400th or so of the capacity of the backbone. The important thing to keep in mind here is that most traffic on the internet is not latency sensitive. You're looking at 70% being video streaming. Bulk of the rest is actually software downloads or file sharing peer-to-peer. A lot of this stuff, most of this stuff is not latency sensitive.
So this would be tagging packets as this is
Yeah.
latency sensitive. Okay.
So that's that kind of thing. The network management challenge, or how you do these things cleverly, is the bunch of technical work. So this is, keep in mind, a raw proposal for a decade-long research agenda. So, yes.
I wonder where to do your experiments. For example, you compare throughput between the Jellyfish and the battery.
Yes.
Where to do it?
So most of those are simulations. We have some results on that small testbed, but most of those are simulations, packet level simulations on my desktop.
So which simulator?
So the simulator is the same as the multipath TCP folks. We just use their substrate to build it.
So for testbed, you have your own.
For testbed, we
small
use these pieces: OpenFlow for routing and multipath TCP actual in the kernel implementation. For
set of some PCs.
yeah.
And the communication pattern is random.
Yes. And we have results for all matrices and for nearly worst case matrices as well.
Worst case matrices? What does that mean?
So finding the matrix that minimizes throughput, finding the traffic workload, that minimizing throughput for any topology is in the hard. But we have heuristics that get very close to that bound. We can show a bound on what the minimum throughput is. And we can test those matrices. So even on those matrices, our topology needs other networks like factories, for example. There was a question there, yes.
Yeah, so you, so this random network is applied for data center only, or
Sorry, I got distracted there.
so this random network like only work for data center network, or can we apply the
Right,
concept
right,
to
right.
rework a network?
So for example, the network design problem we are solving in the wide area with the internet at the speed of light design, that's not a good setting for building a random graph, because there are constraints with regards to where the population is, the distances involved, all that adds a big cost.
So how we deal with the load balancing among server
Right.
parallel also?
Right, so load balancing here is taken care of by MPTCP. Multipath TCP, that piece, what it does is you give it a set of paths,
Yeah.
and it balances load across those paths depending on what the other network conditions are like.
That's TCP is handled at the transport
Yes.
layer, right? But
Excellent point.
at
Yes.
application level, like how
Yes.
we do that?
So the same solutions that you use today for distributing requests across servers should work. There's no reason that you should have to do something different. But your question raises an interesting point. The problem we've solved it at the transport layer, which is in many settings not quite desirable. For example, if you're a cloud provider, you have people with their own virtual machines.
Yeah.
They come with their own transport control mechanisms built in, and you don't have the freedom to change that. So that's a piece that I am actively thinking about in terms of how can you do efficient routing at lower layers than transport. But good point. Do we have?
Go ahead.
Sounds
No,
good.
yeah, yeah.
There was actually yes. Queuing. Sorry.
Nandini was first.
Go ahead.
Oh,
Okay, I'll go. So if I have one takeaway from your talk is that random topology is better than structured topology. That's kind of the two extremes. Have you considered things in the middle, structured
Right.
with randomness?
right. So the in some sense, yes. There are two different answers. One is people have looked at small world data centers, for example, where the small world network idea is you have this lattice that's roughly ordered in some dimension. And then you have some connections that you make for shortening path lengths.
Okay.
It turns out that those things are inferior by about 20% than random graphs in terms of throughput. So we tested that out. So that's one sort of middle ground, right? It doesn't quite work as well. The other thing, the thing we are doing with cabling is actually adding structure, right? We are physically partitioning these things and having fewer connections. It's not quite vanilla random anymore. So
Okay.
yeah, we do need that stuff.
There's a paper that you may want to look at
Right.
from the interconnection network, supercomputer, high performance computer interconnection network in
Sure.
2012,
Sounds good.
adding random links to basically k-ary n cubes.
Right. So that's roughly the direction the small world network work has also gone in.
It's not that small. I mean, they're
Right,
talking about
it's not,
billions of nodes.
not small, so small world graphs are a model of random graphs, not
Okay.
small in the sense
Okay,
of,
okay.
yeah. So that's roughly the direction that is taken, yes.
So I have two questions. One of them is, you're at some level, the mechanisms you're talking about are workload agnostic,
Yes,
right? A more holistic solution, because
Right.
I have to deal with content placement, task placement, and
Right.
a whole bunch of other things, are essentially not necessarily a drive to situations, a drive you towards designs that are probably more workload specific. So for example, when I take my data center and say these racks run high performance computing and this is the
That's
infrastructure
plausible.
I'll do for it.
that's
And-
plausible, yes. If you do that, you'd probably build one section of your data center which is sort of topology agnostic. Now again, if you're building a HPC system, for example, right?
Right.
Most of their applications tend to have very local traffic patterns. You're typically simulating some physical process, like if you think of atmospheric sciences, let's say, your simulation nodes are rooms full worth of air. This room only communicates with adjacent rooms full of air, right? So you can imagine that a topology like a torus, where nodes are connected only to their neighbors, is the best thing you can build. You will not do better. There is just no way you'll beat the topology that matches the traffic pattern. So if you know your applications are going to be of that nature, you're better off building according to that. But if you want to do general purpose design, this is a better strategy. Yes, finally, sorry about that.
So your main observation is that random graphs scale better than
Yes.
structured. in that setting. Do you think this is a surprising finding, or it confirms what was expected from theory? For
So-
example,
Yes.
Your problem is a multi-commodity flow problem.
Sure.
And for a given graph,
Right.
there are results for that. And there
Yes.
are no results for different classes of graphs. For
Right.
random graphs, for and so on. So did you expect what you saw, or were you surprised?
So part of this work is with a spectral graph theorist, Alexandra Kolla at UCI. The overall idea is that people in theory have these results with regards to asymptotic values or order estimates. But most of these differences that we find here, we're talking about small constant factor things. A lot of these graphs, for example, hypercubes are also expanders. They're also flat in the same way. They don't organize in a free-life topology, but we get different results. Right? So this is not something that you'll find is known in theory. So throughput is a property that's distinct from path length. The intuition works, but it's a little bit different is what we find. Cuts matter, path length also matters.
But that relation is also known in that multi-commodity flow framework. So path length
Right.
has a relation to throughput. So
Right. So many of those results tend to be all of these things, or this topology is optimal within a log-in factor of that sort. That's not very useful for us in practice here. Because we are talking about a 25% difference, it's not asymptotically different in many cases. In some cases, there are asymptotic differences. For example, between the hypercube and the random graph, there is a log-in factor. That would be the sort of thing that you might find already in the literature. Mhm. Yes.
I'm with her.
Sure.
And I have a question here because I think there's a trade-off. If I want to route random traffic using
Yes.
random graphs, it's intuitive to wait. Don't jump.
Sure.
Okay? Now, if I have random traffic, I will have congestion. So the bandwidth is not the same everywhere. Bandwidth will change dynamically depending on congestion in the graph. And what people have done, and this is Skype and other
Right.
things like that, they build overlay networks and
Right.
they build regular graphs on top of that random graph to better route. So what is your response to
So
that?
here, the results we show actually show that there's massive flow fairness in these
I
networks.
can do
We don't have-
simulation to prove anything.
We show that the
Right.
gap between the simulations and the test bed that we are running is very small. That's the best we can do at this point. We
Yeah.
don't have
Did you
hundreds of
consider
servers.
the variable, the dynamic bandwidth?
Right. We find that a very small fraction of flows will still face congestion, but this is very similar to the fraction that see congestion in a factory, for example. So there is this thing that people compute, right? Jam's fairness index across flows. We find that both topologies produce very similar values. So the distribution of throughput across flows is actually quite even. So we do investigate those things.
Well, I don't doubt that you're investigating.
Sure.
I want to know what.
Yeah, the result
happens.
is
Yeah.
actually nice, that
Okay.
throughput is even.
The last question.
Yes.
On your new work,
Yes.
when you say at speed of light, you're really talking because at the edge you have all of these other wireless networks.
Yes.
You're really talking to somewhere near the last by
Yes.
one or last
So
by
the
two
map
miles.
I flashed here,
Uh-huh.
it only talks about connectivity between cities at the sort of macro level. The last mile problem is too expensive to solve at a speed of light latency. So you'll have small constant overheads over 5 milliseconds getting to that place.
Actually, it's interesting, because microwave towers at the smaller distances would not be that. I mean,
Right, it's
you could
just
potentially think of putting more of those in the
That's true.
metropolitan area than
That's
you would
true.
in a cross-country network.
it's plausible, yes.
So, I mean, I know that they considered it here when we were talking about, connecting.
A little bit of care is needed here because these things are directional. So you'd have, for
Yeah,
each home you would need one dish if you were to do that.
No, but I mean,
So-
yeah, it could be concentrated as a cluster. and then-
Right.
Yeah.
So
So
that
you're
kind
right.
of thing is
Yeah.
plausible, yeah.
Okay, well, thank you so much.
Thank you.